All right, so let's get started. I am sharing a screen with the iPad so I can take some notes here, and we'll see how that goes. I hope it's big enough to for you to follow. So maybe change the direction. So yesterday we discussed or introduced the idea that in quantum mechanics, where we solve some Schrödinger equation, we can get the wave function, right? And by solving this equation, right? So this is an eigenvalue equation. You should have discussed this in your math courses, right? It's a differential equation, so the solution is not trivial, but there are ways to find these solutions. And more importantly, conceptually, this means that we can calculate and predict what the electrons do, right? So in particular, suppose you have an atom here with a nuclear charge equals Z, and then you have another atom with another nuclear charge. Let's call it Z1 and Z2, right? And these nuclear charges Z could, for instance, correspond to fluorine and hydrogen. Then you would expect to form the molecule HF, right? Then you can ask, where are the electrons? What do they do? How do they look like? Okay. And the solution of the Schrödinger equation will tell you, in the sense that once you've solved and you found this function psi, right? Psi is a function of space, right? So that's the little r, and you have that for all electrons. So I should put a little I for all electrons, and I'll make it a set, right? Now I'm lazy and I drop this argument, right? And that's how you get this H Heugabel equals E Heugabel. But of course, the H is an operator, so it acts on your wave function. It transforms it somehow. In particular, you know, we've discussed H yesterday. There are differential parts in it. So you are supposed to take the derivative, okay? And then it turns out, if you do that twice, you get back your original function, and you get in front of it some prefactor, and that's the eigenvalue. Now, the function, right, that responds in such a way to the differential operator, and this you also know from high school, that function is called the exponential function, right? You also know that sinusoidal functions, when you differentiate them, they recover themselves, right? They change the sign. You go from cosine to sinus to cosine and so on and so forth. So think about this, right? These are the functions that you could imagine taking the place of psi, right? So psi is nothing abstract. Psi is just a symbol that we use for convenience and to describe the general case. But it's not some fancy weird quantum function which is somehow esoteric or anything. It's just a normal function. Think of it as something exponential. In particular, for the free atom, your psi could look like something exponential. And so you also know immediately what kind of exponential this could be, right? Now, where do the electrons go most? They go where the protons are, right? The opposite charge. That's where you should have your maximum. And then you have an exponential decay. So nothing complicated about imagining an exponential decay for your electrons. And then you also have a little one for the electron around your hydrogen, right? So this could be your psi. And now psi, there is this little complication that psi could be complex, right? But there's good news in this, that if we take the square of psi, so the probability of psi, right? Then you don't have to worry anymore about it being complex or not, right? That's a real number. And this as a function of space again. And now I drop the little I, right? Because anywhere in space, I know there could be electron 1, 2, or 3, whatever. I don't care. We'll just sum them up, right? So suppose that's our psi squared, and that's our electron density at R. And now for completeness, I must introduce the axis R, right? And what do we have here on the vertical axis? It's our charge density, right? These are our particles, right? You could also call it N. So let's call it particle density, right? Now, this Z1 is the particle density of your protons. It looks a little bit like a delta function with the height corresponding to the number of protons, so your nuclear charge, right? Now your electrons, they smear out all over the place in this exponential way. And but if you integrate them, right, the integral over rho of R, well, that must be the total number of electrons you have in your system, right? So that's the number of electrons in your system. Right? So if you have HF, right, you'd have 7, sorry, you'd have 9 electrons for fluorine and 1 for hydrogen, summing up to 10 electrons in total, right, for HF. So for HF, any must be 10. This is the electron density which you can measure in an X-ray experiment, right? And that's the picture I showed you yesterday. This molecule is adsorbed on a surface, right? That was a picture of this electron density, right? So this is something quite specific, right? And you should wonder how is that linked to what we observe, right? How is that linked to, let's say, arguing that the CC bond is stronger than the CN bond, or vice versa, right? That observation should result from this underlying electron density, right? And so that is what this course is about, right? Now let's go back to these slides we started yesterday, and switching screen now. So here are the slides we discussed yesterday, and as I said yesterday, I will still share these. You will have them later on today, as well as the video recordings. So we have this derivative of the energy, and we discussed yesterday that the energy is the expectation value of your Hamiltonian. And so first you solve Schrödinger's equation, you get that wave function, right, as a solution to the eigenvalue problem. And then you multiply this product of H psi with psi once more, you integrate it, and that gives you the energy. And then you can ask this question, now, how does that eigenvalue change if you change a little bit something in the Hamiltonian, right? And that first order derivative you see here is equation 7. And I'd like to tell you now how it looks like, right? That's now shown here in equations 8 to 11. And let's walk slowly through this, right? So here you have the derivative operator, the differential operator, working on the energy, right? So the energy is this expectation value. And if you write out this expectation value, it's the integral over all the electronic degrees of freedom. And this is what this tau stands for, right? So tau is the collective volume variable in which you're moving here, in which you're calculating your psi, right? So this means the small I and the small r. You're integrating over small r for all i's, for all small i's. That's what the tau then represents as a volume integral. And we can now see that the differential operator goes through this volume integral, right? You can pull it inside the integral. And then you have a product of, basically a product of three things, right? You have your psi star, so that's the complex conjugate of your wave function. Then you have the operator, and then you have the psi n, right? And so you have these three terms, and this is nothing else than the product rule, okay? So equation 8 is the product rule of your differential operator, working now on these wave functions. And we are doing this for a certain solution of Schrödinger's equation. Now, you know that there's more than one solution, right? You discussed, for instance, the particle in the box. You already discussed the harmonic oscillator. You know that there's more than one solution. You have a spectrum of possible solutions. And we like to index these solutions with a small n, right? So for the solution n, right, you see now that you have to take derivatives, and your Hamiltonian does not depend on your solution n, right? But obviously your wave function depends on the solution. And so you apply these operators to each solution. Now, if that is your ground state solution, then n equals 0. Or 1, depending on where you start to count. But it's obvious that as such, this Hellmann-Feynman derivative also works for the excited states, not only for the ground states, right? But it is most commonly applied to the ground state. Now, let's look at this integral first. What is this? Well, here your operator, your Hamiltonian operator, is working on the solution to your Schrödinger's equation. So that just gives you the eigenvalue, En, right, times psi n, right? So in other words, there's a number here. This becomes a number times psi n. And if a number, you can always pull in front of the integral, right? So here you have your En in front of the integral. That's what's left over from your operation. And we didn't touch this, this derivative here. Okay, then the middle term, we have to differentiate the Hamiltonian. We're not gonna, this is the same as in the line above. And what happened to the right-hand part here? This is most interesting if you compare the right-hand part in line 9 to line 8. Somehow this Hamiltonian operator ended up on the left-hand side of your complex conjugate wave function. Okay. And you know that operators, they always operate to the right, right? So how did that happen, right? Are we allowed to do this, right? This violates the basic rules we have for operators. And this operator now, together with psi n, they go into this bracket, and the whole bracket is complex conjugate. Now, this is a special property. So in general, that's not allowed, okay? So for the general operator, you cannot operate to the left. There's a special class of operators. They're called Hermitian operators. They, for those operators, you're allowed to do this. And now you can ask, what is a Hermitian operator? It turns out the Hermitian operator, any operator which has only real eigenvalues, any such operator is Hermitian. So meaning any such operator can work to the left as well as the right. Now it turns out that the Hamiltonian is a Hermitian operator. Actually, most operators relevant to chemistry and physics are Hermitian operators, meaning that these eigenvalues, which come out as solutions, they're always real, right? Have you ever seen a complex eigenvalue to a quantum problem in chemistry? Never happens. right? So you're pretty much on safe grounds. The good news is, while mathematically, formally, you're not allowed to always to operate also to the left, in practice, in our field of science, in most cases, we are allowed to operate to the left. In particular, for the energy, completely safe to work towards the left. And so instead of evaluating the operator working on this derivative, which we don't really know what it means, this deep psi d lambda, right? We don't know how psi depends on lambda. That should be awfully complicated, right? Instead of evaluating the operator acting on that complicated object, we just let it operate to the left where we know the solution, right? So if you just look at this little bracket here, what's inside here, this is again the Hamiltonian working on the solution, operating on the solution to our Schrödinger's equation. We know what this is. This is the energy. And we said we're allowed to do this because it's Hermitian, and it's Hermitian because it has a real eigenvalue. So the complex conjugate of that solution will be a real number, which is the En. Okay. So that's just our number, and we're left with our complex conjugate here. Now look at this last term here, right, in equation 10, and the first term in equation 9. They look awfully symmetric, right? On this first term, in both cases, you have the energy in front of it. And in one case, you have the derivative of the complex conjugate. In the other case, you have the derivative of the real component, okay? Now, that must be the same as saying, I'm gonna differentiate the product of these two wave functions, and that's what you see here, right? If you just take, I don't know what it's doing, I don't know. If you now differentiate this integral here, right? You have the product and you apply the product rule, you get once the derivative of psi star and once the derivative of psi, right? And in both of them is En, right? So that's where you can collapse these two terms by pulling the differential operator again in the front, right? Okay, now if you look at this integral, this is the integral of the inner product of the wave function, right? And this inner product, we know this gives the electron density. And if you integrate the electron density, what do you get? You get the number of electrons. Now, how does the number of electrons depend on lambda? It doesn't. It's a constant, right? So you're differentiating a constant with respect to lambda, and that's 0. So this entire second term here must be 0. And hence, the only thing that's left over was the center term here, where we take, which is nothing else, we can identify this, it's nothing else than the expectation value of the derivative of the Hamiltonian. And that's what you see here on the right, right? Okay, is this clear to anybody, everybody?
Can you just quickly repeat what you said for 10 to 11, the second part, how you collapse those two parts together again?
Yes, let me write that on the blackboard, because that's actually easier. So if I take the derivative of psi, this is the same as taking the derivative of d tau. Right? So this is just bracket notation. I presume you're familiar with that. And tau now contains basically, for all my electrons, I, right, all the coordinates, and it also includes, for each electron to be very formally correct, its spin, okay? you're integrating also over the spin variable. Right? The behavior of your wave function also depends on your spin. Right? It should be obvious if you think of magnetic properties, just think radicals, triplet, singlet sort of chemistry, then it should be clear very different species. It's because the wave functions of these electrons depend on the spin which you have, right? All right, that's all included in your tau variable. All right, so now I pull my differential operator inside the integral. Right, so now it's working to the right on this product, and yeah, maybe you're not so familiar with this. This is the same, right? That's my notation. I define this as being this. Okay. So now you're operating on two functions, right? And that means you have once d lambda psi multiplied with psi and once lambda psi. Right? That's your integral. Right? And that's, if you write the energy in front of the whole thing, right? That is then identical with these two terms. So I just factored this out, right? And that those were the two terms you got in this expression. For the, so basically in the proof I just showed you, we went the other way around, right? We started here and then we made our way up here, and then once we arrived here, we know that this must be 0 since this here is a constant.
All right, thank you very much.
No problem. Thank you so much for asking. It's really good that these things are clear. Any other questions on this? If that's not the case, I'll go back to our slides. And again, you see the final result of our derivation. And so these couple of steps, right, they require the formal background on the quantum mechanics, right, with our wave functions, our spin states, and so on. We included all that. And then by application of product rules, simple product rules, you arrive at what Hellmann and Feynman and others have shown just 100 years ago or so. Now, we started out by, in the first point here, by asking, how can we use this for the force on the atom, okay? And this is what you see now in this last line. So suppose now our lambda is the position of the atom, not its nuclear charge, and not of atom J, but just of atom I in the direction X, right? Every atom can move in 3 directions. And so we want to get that X component of the force, right? So this means we have to differentiate the Hamiltonian of our system with respect to the X entry of atom I. And if you remember, we discussed the Hamiltonian. You know this Hamiltonian now, which just by the way is typically a question I like to ask in the exam. How does your Hamiltonian look like? We know there's this external potential, and as one of you pointed out yesterday, there's a sum missing here, but here you have your nuclear charges, and here you have your coordinates. Now this is a vector, contains x, y, and z, right, in your norm. And now we need to differentiate that with respect to the capital Xi. Now I would suggest to you, for instance, until tomorrow, you can ask Moss and Mr. Trestman in the exercise hour, how to differentiate this norm of a vector distance vector. This norm has to be differentiated, and it is in the denominator, right? Now, if you do this correctly, and you should absolutely try to do this, you will arrive at an expression where you have the distance to the power of q of 3, so cubed, and you will also have the distance vector of the x component. So just the difference in the x components, right? And your two wave functions here, they collapse to the electron density. So you have to multiply the electron density with the external potential part, which was the Zi. And then if you differentiate the 1 over the distance with respect to capital Xi, you will get this x distance over the full distance cubed. And then, of course, there's also similarly the derivative of the classical nuclear potential, right? And that's the force on your atom, right? And you see that all you need is the electron density. If you have the electron density, it will spit out the right force. So this is an illustration, right? This is an example of how important is the quantum mechanics of your system for chemistry, right? You have here the exact formula for what the forces on your atom are in any given compound. Doesn't matter which compound, right? It's fully general and universal. It also illustrates the appeal and the power of and the promise of quantum mechanics, right? Any compound, right, has a force which looks like this, right? So we know the equation, right? So chemistry is solved from the fundamental point of view of physics. There's no problem in chemistry. It's not a scientific problem anymore. It's an engineering problem, if you wish. So you might be disappointed, and you might come to the conclusion, well, then I was born 100 years too late. I should study something else if I want to become a scientist, right? Now, to that I would answer, not so fast, right? So there's still some problems, right? And it's maybe a little bit similar to when Planck was thinking about studying physics, and somebody told him that actually all problems in physics were solved. There were only these minor little inconsistencies nobody really knew, but physics was considered solved. Boy, how wrong were they, right? So there could still be really major discoveries ahead. And part of this lecture is also to sort of alert you to the fact that there are things missing, right? I don't want to tell you what's in the textbook only, right? So in the textbook or in high school or in lower degree courses, people tell you about all the things we understand and we know, I'd like to also bring you up to speed so that you can at least appreciate all the things we do not know. So, this sometimes comes as a surprise, but there's much, much more we don't know than what we do know. So we do understand fairly well chemistries of very few atoms. I mentioned that yesterday. But as you get to the heavier elements in your periodic table, right? So I hope you all have something like this at home. It's the alphabet of the world of matter, right? As a chemist, you should have that if you don't know it by heart. We know very little, maybe about these elements, a couple, not too many of those we can deal with for the ground state, not for the excited states, right? And that's about it. Okay. So there's much, much more we don't know. All right. So that brings me to, yes.
When you go back one slide real quick, aren't there supposed to be three? I mean, in the Hamiltonian, like three things that are added together. Here are only two. I mean, like the kinetic one, the external potential, and then also the interelectronic one.
Thank you so much. Yes, so you have these three parts, right?
Yes. Now,
you're completely right. We have to differentiate all these three parts. But we are interested in the force on the atom I. Right? So where does the atom I show up in your Hamiltonian? Not here. This is the electron, small I, right? This electron does not explicitly depend on the position of your nucleus, right? Mm-hmm. Same here, right? That's only electron. So it's only in this external potential term. And I'm really sorry that one of the summation symbols is missing. I'll correct this before I upload it. It's only in this term that your system is specified. Okay?
I see, yeah.
So it's very important, and I'm so glad that you're asking this question, because if you look back here, right, all of this is system specific. It's for the specific geometry, right, for the specific nuclear identities you have. And in your Hamiltonian, the only place where this shows up is the external potential, right? Here you see the nuclear charges, and here you see their positions, right? So what Hellmann and Feynman had in mind then, right? And what's so, in some sense, it's the relief and the coolness about the Hellmann-Feynman theorem is we don't have to bother about derivatives of these other two terms, right? It's only this external part.
Mm-hmm. All right. And the differential part of the potential and the second part, where does that one form? I think it's in the last slide that you just opened up.
This one?
No, just in the very last slide that we just covered.
Here?
Yeah, where does the second part show up?
This is the nuclear repulsion part.
All right, yeah. Mm-hmm.
So the nuclear repulsion part is sort of trivial because you don't need the wave function for this, right? You don't need the solution to the electronic Schrödinger equation. Right? So people like to drop it. They don't talk about it. But of course, you need to add it afterwards to get the kind of binding potential which compares to experiment, right? But from a conceptual calculational point of view, it's trivial. It doesn't depend on the wave function, right? Mm-hmm. Okay, we wrote it up here. So that's important, right? Here, your total energy is the complicated electronic one, which you get from the solution of Schrödinger's equation, plus the simple function where there's no wave function in it, right? It's literally, you have your 5 atoms and you literally sum over all pairs of them. You multiply their nuclear charges and you divide by their distance. Mm-hmm. Right. So if you can evaluate a distance in real space, then so, right. So that's yeah. If you have just two atoms, you can nearly do it in your head, right? Okay. Thank you so much for these clarifications, right? It's always good that you're asking these, because as a professor, we forget about this, that this is, that you see this for the first time, and so we forget that you don't see that this is trivial, right? But of course, you're completely right. One has to point that out.
Sorry, as a quick note, if you'd like, we can go over this tomorrow again. It's straightforward.
Thank you.
Okay, so what you have now, what we got just obtained in Hellmann-Feynman is the analytical expression that gives you the slope on the surface like this, right? So you can use this derivative. You can look, for instance, as you change your coordinates, where are the forces zero? If the forces are zero, you are either in such a minimum or in some saddle point. Okay, so you see how powerful such a derivative can be, right? And how instructive, right? It really, if you wish, probes the degree to which you understand the problem. Okay, so if this is also great, and if this works also well, why don't we just calculate it all, right? And that brings me back to this case, why to all the systems we don't understand, right? We understand very few systems, but what is the problem then, right? Well, so this is a recent snapshot from the Chemical and Engineering News, which is sort of the newspaper of the American Chemical Society, which is the largest society of chemists on this planet. They looked at, there was a paper by Daniel Singleton, who is an organic chemistry professor in Texas A&M. They did a very in-depth study on the reaction mechanism of the reaction you see up here. It's a condensation of this carbonyl group with this double bond. And it's a multi-step reaction, okay? And so they were wondering how good is theory really, right? How good are these calculations when we compare them to experiment? And so it's a very fundamental question, right? And very important. And you can see it's just 2015, right? That was yesterday in terms of science, right? Maybe for you it was when you were still in high school, but this is as good as yesterday. And what did they find? They first of all measured with great detail and spectroscopical experiments. They got this black line, which is what we believe the most accurate reaction profile for this reaction. So you see these multiple intermediate steps, right? You see that overall the reaction energy is negative. So the thermodynamic driving force is there. And the barriers are not too high. So kinetically, this is definitely possible for this reaction to happen, right? So scale-wise, right, 20 kcal per mole as a barrier, that's roughly 1/5 of a covalent bond, right? A covalent bond, single bond or so, is 100 kcal per mole roughly. So you have to overcome this 1/5 of a bond to have this reaction happen. Now, what you see in terms of colored graphs here are the various density functional theory predictions. So these are numerical calculations that try to predict the barrier, right, by solving the electronic Schrödinger equation. Right? And as you can see, they vary vastly, right? And they vary to a degree that you could argue if you don't have the experimental curve, you wouldn't be able to tell what's going on yet. Right? It all becomes a big envelope and anything in there is possible. So you cannot really do chemistry with this, right? And this sort of describes the problem we have, right? We are not predictive enough, right? The theories we have, the framework we have, we know it's founded in rigorous physics, it's correct, but it's not accurate enough. The quantitative predictive power is not good enough for us to do chemistry with it. So in this sense, our understanding of the quantum mechanics of electrons is in most cases unsatisfying. Okay, and that is really the challenge that is still going on. So why is it so complicated? What's the why is that, right? Why would there even be multiple solutions or multiple estimates? Well, we have to make approximations when we solve Schrödinger's equation, because if you just think about the properties of a wave function, right? It's an immensely complicated function. I just said it's just an exponential function, but that's a qualitative description, right? It's an exponential decay, and we know it contains these terms, but we don't know the exact shape, right? We don't know its exact form, right? That would allow us to predict energies down to 1K Kelper-mole in terms of deviation from experiment. So why is it so complicated? Well, its complexity grows dramatically with number of electrons, right? Because all these electrons, they are distributed in space and they all interact with each other, right? Simultaneously, right? So it's it's a function really that depends on the NE electrons, and each electron has 3 degrees of freedom and the spin, okay? So we have 10 electrons, let's say in HF, that gives us 4 times 10 dimensions, right? So it's 40 dimensions functions just for HF. Okay? Let's not mention throwing it into water and adding some salts. So that's the mathematical horror behind chemistry, right? So this is what's written here. And then this function also has to do something really nasty. It also has to obey the anti-symmetry condition from Fermi, right? You know this. If you flip the coordinates, you've had this in your preceding PC lectures. If you flip the coordinates of fermions, this entire function has to change sign. So imagine you have some experiment, you shoot out an electron, okay? Then you shoot out a second electron, and then you throw them in again, okay, with an electron beam. And under some circumstances, to some parts in this experiment, they will have exactly changed location. Once that happens, this entire wave function changed sign, okay, everywhere, right, simultaneously. Now that's a very peculiar thing, right? But we know experimentally it must be like this. It's the Stern-Gerlach experiment. You can do this, and it must behave like this. Okay, so that's a law of physics, just like gravitation, right? You don't argue with that. All right, so it's just another property this function has to obey, and that makes this function a very weird function, right? Now, we also know that with this Hamiltonian operator, when you evaluate the eigenvalue, this function must be minimal, right? So that's also not obvious, right? So you could throw in any trial functions for this psi, but we know that if you do the solution, then there's a minimum for the expectation value of this Hamiltonian operator, right? It's completely unclear what this means for the function space we can use. Then it must also be possible that when we integrate the inner product, that we get this constant, which is the number of electrons. And then if you just think about the bits and bytes you need to store something, you will rapidly see that this is quite impossible. So imagine something like 10 orbitals, right? So this would be 20 electrons. So HF dimer or water dimer, right? Just 2 molecules. They would have 10 molecular orbitals. Each orbital has 2 electrons. Now, suppose you store each orbitals on 100 grid points. And that's not a lot of grid points, right? That's not even 10 by 10 by 10, right? In X and Y and Z. That would be 1,000 grid points. Suppose you get away with just 100, okay? That means then, because you have 10 orbitals, that you would need 100 to the power of 10 points. If you assume that every value of the orbital you store consumes something like 4 bytes, you're talking 300,000 petabytes, okay? Now, 1 terabyte is roughly 100 Swiss francs if you go in the shop and buy one. 1 petabyte is 100,000 Swiss francs. And so this whole thing is 30 giga Swiss francs, okay? So billions. So you have to be a billionaire to store a coarse version of the wave function of something like the water dimer. Okay. So I let that sink in, right? we reached 10 o'clock. I'll upload the material today, and I wish you a lot of fun tomorrow in the exercises, and I'd like to thank you for your attention for today. Bye-bye.
Thank you very much. I just have one other request.
Yeah, sure.
The slides, is it possible to have them before in the lecture? Because I like to make notes inside the slides.
I'll upload them today, but as I explained yesterday, I prefer for you to take notes by hand, and so I'll hand out the slides always afterwards.
Okay, thank you.
No problem. Bye-bye.
Goodbye.